Well, hello, my name is Mark Gray. I'm with the Construction General Permit Training Team, and I'll be covering Module 14 today, total maximum daily load compliance requirements for the Construction General Stormwater Permit. Our module learning objectives today are to understand where and how TMDL requirements apply to a responsible dischargers project with coverage under the 2022 adopted Construction General Permit. And I will say that TMDLs have been around for many years now, more than 25 years, and have been incorporated into a number of municipal and general permits. The most closely related is the California Industrial General Permit, which was renewed and adopted in about 2015 to 2017 and included total maximum daily load requirements. The last reissuance of the Construction General Permit, TMDLs were mentioned but not specifically addressed via compliance requirements. And with the 2022 renewal, now they are included in the permit, and thus we're covering it today and in this renewal training. So the other things we're going to do in our module learning objectives about TMDLs, in addition to how they apply to responsible dischargers project, and that is this responsible discharger is a newer term that's been modified in this 2022 CGP. We'll want to understand when these provisions that help define the compliance process for a responsible discharger. And there's three primary conditions, and you can see them here on the slide, and I'll cover those in detail here in a moment in a nice figure that summarizes that relative to the location, the types of pollutants, and then the process that's used when it's triggered for monitoring, if all those three requirements converge. And we'll want to understand in this module the best management practices, the BMPs for soil erosion and sediment control and treatment that are deployed to meet the TMDL compliance requirements. And we'll go through a slide of those in detail and integrate those into the discussion today. We're going to want to understand the monitoring and reporting process and timelines, because there is that you'll need to use that are within the permit, regardless of whether or not you would have an exceedance of the value that's included in the TMDL compliance requirements, and those are related to numeric action levels and effluent limits, and we'll get to those here in a minute as well. And then we'll want to understand the consequences of non-compliance with the TMDL requirements when your non-visible pollutant monitoring sampling results show an exceedance, and what the consequences are. So let's move on and get right into it. Let's first start with the definition of a responsible discharger, and I will read this slide. Not all slides I'll read, because this is a word-heavy presentation. And I will say here to all the students taking the renewal training that much of the words and phrases that I've used today here in the presentation come right from the permit. So a responsible discharger for a TMDL is a discharger that discharges stormwater and authorized non-stormwater directly or through a municipal separate sewer system or other conveyance to impaired water bodies or watersheds identified in a US EPA approved TMDL and has one or more TMDL specific pollutant sources present on site with the potential to enter construction stormwater discharge, which are required to be identified in the pollutant source assessment. Now, that's a long definition, but one that's really important relative to TMDL compliance. And of course, we've underlined the key areas of our drainage system where these apply. So what are the TMDL pollutant categories? And these are categories of pollutants. This is not a complete list of the total maximum daily load TMDL pollutants that you will encounter in your work. These are the categories. And here we have bacteria, chloride and salts, diazinon, which is an organopesticide, various nutrients, most primarily nitrogen and phosphorus related TMDLs, sediment, which there are many sediment TMDLs up and down the state of California, temperature, TMDLs, metals, and most of these are related to urban area metals issues, lead, chromium, copper, zinc, commonly associated with automobiles and other industrial sources, and then several different kinds of toxics, some legacy organics like PCBs and other types of chlorinated compounds where there are TMDLs in place, and these are primarily in place in Southern California and in a small area of the Bay Area. So see attachment H for a complete list of the pollutants. Well, now moving on to when do TMDL compliance requirements apply to a responsible discharger? And you have to have three conditions must be met in order for these requirements to apply to your project. And the three are they're shown in this I think a really good simple figure. So take a few moments to understand the figure, and then each of these circles or bubbles that you see, I will go into more detail on each of those areas. So number one, the project, your responsible discharger, you have to discharge to a TMDL watershed or water body that has a pollutant which has a numeric action level or a numeric effluent limit identified. And I will define those action levels and effluent limits here in a moment. If you are in one of a particular area, your pollutant site source assessment, the TMDL pollutant needs to be identified in that source assessment with the potential to discharge. And we'll go over that pollutant source assessment here in a moment. And finally, during rain events, during storm rain events that trigger discharge, you will, in order for the TMDL compliance requirements to apply, your non-visible sampling requirements would have to be triggered. And those triggers are such as spills, breaches, or BMP malfunction and failures. And I will go over those definitions and how that non-visible pollutant sampling requirement process works here in detail in just a moment. All right, so getting to the requirements of each of the three circles, let's talk about permit requirements for TMDL compliance. As I mentioned before, you need to use and be very familiar with attachment H and table 2 in attachment H2 to determine if your project is within a TMDL pollutant water body combination, and then what the compliance actions are. And I've provided the link for the state program so you can clearly see what that is. And I believe in the future that for those of you working in this area, the state is contemplating providing a sort of a geosource tool, a graphical information system, GIS tool, to help dischargers identify if their project is in a TMDL pollutant and water body combination. And then the requirements for TMDL compliance, each TMDL pollutant will then have a specific best management practice implementation requirement that you have to deploy, such as using the soil erosion model, Russell 2, use numeric action levels, numeric effluent limits. There are a few other best practices, and we'll go into those in detail here in a moment, but you'll see the reference there. There are detailed descriptions in attachment H and also in the fact sheet that you should refer to. And finally, the permit requirements in certain areas. If you are in depending on your location, your water body, the pollutants that have the potential to discharge, you may have to conduct a TMDL pollutant source assessment as part of your stormwater pollution prevention plan requirements. And all of you are likely very familiar with that, and I've provided a reference to that in the order, the adopted order. The other permit requirements for TMDL compliance have to do in that three bubble diagram, three circle diagram, are the non-visible pollutant runoff sampling and monitoring requirements that are triggered that could result in the potential for a pollutant to be discharged. And that trigger is due to a failure to implement best practices, a container spill or leak, or a BMP breach, failure, or malfunction. Now, those terms are not defined exactly and specifically in the construction general permit. State board staff advised to use the Webster's definition of those various failures or actions to provide some guidance and interpretation. And I think one of the areas that QSPs and QSDs and all who are involved in construction site compliance with TMDL requirements will have to pay attention to how these triggers are exactly defined, because there is some interpretation of those terms due to lack of definitions. And then finally, there are some specific smarts the computerized reporting system that the state used that also you're all familiar with. There is some specific reporting and deadlines, including when you need to provide and prepare an a numeric action level or effluent limit exceedance report. And I have a whole slide on that as well here coming up. All right. Let's talk about the pollutant site and source assessment and soil screening and sampling when applicable. And there's really 4 elements to this. And again, this is a very logistically specific requirement, primarily that would be done within regions 4 and 9 in Southern California, where TMDLs apply, that we would have to do a pollutant site source assessment. And so there's, as I said, there's 4 main elements to this. You have to have the potential to discharge. You have to develop a list of pollutants based on a review of the site, of what you're going to be doing on your construction project, including the materials, the types of soil amendments, and if you're bringing in any other kind of a product that would potentially include, say, a copper, zinc, nitrogen, phosphorus, fertilizers like that. And then you also have to look at historic potential contamination at the site, which relates to the 3rd bullet. It would be, you'll have to do some type of environmental and a real estate documentation or review to determine if those pollutants had been on the site due to past land use practices. And then if you identify, if you're in those areas, you may have to conduct soil screening and sampling within some of the TMDL watershed and water body combinations. And I said earlier that principally in region 4 in the Los Angeles area and region 9 in the San Diego area. The best management practices that are used for TMDL pollutants span a range of types of best practices, from traditional site-specific sediment and erosion control best practices that are commonly used throughout California. This permit and this new revised permit and the inclusion of total maximum daily loads have brought in some other types of best practices to be used beyond traditional site-specific sediment erosion controls, such as Russell II modeling, which is a soil loss modeling approach that was developed by the United States Department of Agriculture Natural Resource Conservation Service for farming and watersheds. And it's been principally those types of activities that has been adapted to construction sites. And then this, the 2022 adopted permit has also brought in numeric action levels and numeric effluent limits for TMDL pollutants. I'll define what those are here in a moment. Now, the new permit includes passive sediment treatment systems, the allowance to use those types of systems subject to conditions. There's a whole separate module on that, as well as active sediment treatment, which has been allowed in California subject to conditions that are defined in the construction general permit. Both the last permit that was adopted in 2012 and became effective in, or excuse me, 2010 became effective in 2012. Active sediment treatment can be used to meet TMDL pollutant requirements. And then some dewatering systems are also best practices that can be used. Dewatering chemical treatment systems can be used to meet TMDL requirements. So that's the list of BMPs that are used in the permit to provide a pathway to compliance for total maximum daily loads. All right, let's dive in a little more to non-visible pollutant monitoring, known as NVP, abbreviated NVP, and its relationship to TMDL monitoring. And in preparing this presentation, I had discussed with a number of existing practicing QSPs and QSDs about non-visible pollutant sampling the requirements in the past permit, how often it was done, what was done. It has been used very sparingly, very infrequently in California, according to the QSPs and QSDs that I talked to in preparing this presentation, and then reacting to what the construction dischargers such as yourself taking this class, what we're reacting to in the permit. So this will be, we can anticipate kind of a ramp up or expansion of the non-visible pollutant monitoring sampling requirements as a result of incorporating total maximum daily loads. So the NVP runoff and sampling monitoring is required when there's a trigger that results in the potential for a TMDL pollutant that you've identified on your site. You're in a TMDL water body, it's there, you know it's present. And if you have a failure to implement BMPs, you have a container spill or leak, or you experience a best management practice breach, failure, or malfunction during a rain event, that would trigger a TMDL pollutant monitoring. And then you'll be subject to sampling requirements. And I won't go into each of these in detail because you can read these on the screen, and there's some time period requirements that you have in order to comply and relative to sample collection times. And I'll point out the last bullet is a potential compliance pathway is that if you can fully remediate or implement repairs, maintained or replaced immediately after the breach, you are allowed, or you are not then subject to further sampling requirements after that BMP has been immediately in a sense dealt with in time period defined in that section 3D3B. Sorry about that. All right, moving on to definitions of numeric action levels and effluent limits that you would be using if you had a discharge from your site during a BMP breach, malfunction, failure, or container spill or leak. Responsible dischargers that have TMDL related numeric action levels or effluent limits, you must collect samples in accordance with the NVP requirements, and then compare the analytical results to the applicable numeric action level or effluent limit, which is specified in attachment H. So those are concentration limits. And I will read these to you and then have some commentary after it. But a numeric action level is a level that triggers a required evaluation of the effectiveness of best management practices implemented on the subject construction site, and the required implementation of additional corrective actions necessary to reduce the subject pollutant below the numeric action level. And this action level applies to each sample location and our corresponding discharge location. An exceedance of an action level isn't a permit violation, and as compared to a numeric effluent limit, which is a technology-based or water quality-based effluent limit established for discharges covered under the construction general permit, also known as the order. And these compliance location, the effluent limits can apply at each sample or discharge location, including the point of discharge from an active treatment system if you're using it. And an exceedance of a numeric effluent limit is a violation of the permit. And if you do exceed an NAL or an NEL, there is specific requirements for what you need to do. So a numeric action level exceedance occurs upon the second and each subsequent analytical result for samples taken from any and all discharge locations within the same drainage area during the same reporting year and taken in accordance with attachments D and E that's above the set concentration. And for numeric effluent limits, this occurs as well. And recall from a couple slides prior, there is a set time period when you've got to do that first and second sampling actions. Now, if you do exceed a numeric action level, it is not a violation of the permit, but you are required to follow up with the numeric action level exceedance report. And I'll talk about that more here in a moment. Now, for numeric effluent limits, each numeric effluent limit after the first instance on your second sampling is a violation of the general permit and subject to mandatory minimum penalties. The current federal penalty is above $60,000 per year. So there is severe financial and legal consequences with exceeding a numeric effluent limit. So the exceedance reporting that's required whenever if you do exceed an NAL or NEL, you've got 10 days after the analytical result to prepare that report and upload it into SMARTS. You've also got that if you do exceed a TMDL related action level, and if requested by the regional board, you've got to respond within 30 days. And then all dischargers that exceed an applicable TMDL related numeric effluent limitation, and that's an NEL, shall comply with the water quality based corrective action requirements, which are in section 6Q of the order. And for that area, for the water quality based corrective actions, which is a new requirement in the permit, whenever your analytical results indicate that the discharge exceeds the TMDL related NAL or NEL, you are required to determine the source of the pollutant and immediately implement corrective actions. And then the corrective actions are derived from 40 CFR 450.21 through 450.2312. I would highly recommend that students download the latest, or students and people that are taking this module, that you familiarize yourself with those requirements. And they are principally a review and analysis of the on-site specific erosion and sediment controls and implementation of BMP best practices that I listed earlier in the various BMPs that you can use to comply with the construction general permit TMDL requirements. In other words, 40 CFR 450.21 through 2312 really reinforce what's in the existing CGP relative to the actions and steps that you would need to take if you had a numeric action level or numeric level exceedance. What are the corrective actions that you need to do? And that 450.21 through 2312 go through that list of actions that you as a discharger need to employ. And they really work hand in hand with what's in the existing the newly adopted construction general permit requirements. So moving towards wrapping the TMDL module up, there are, for familiarity, there are some important TMDL compliance deadlines and differences that you'll find as a QSP and QSD working on the construction permit. And you'll want to refer to attachment H, table H2 for that. Some dischargers will not have to comply with TMDL related effluent limits or action levels until the specific watershed water body combination compliance deadline comes into play. And these can be different among the various TMDLs listed in attachment H. And also for some TMDLs in the region 4 and region 9, there is a soil screening and total suspended solid surrogate reopener clause that will impact TMDL compliance in really beginning in 2028 and moving into 2031. And I've got an example on the next slide that shows the different numeric action level and numeric effluent limit compliance deadlines for a subject area in the Los Angeles area harbor waters. You have the same water body watershed, the Dominguez Channel Torrance Lateral, but for copper and also zinc and lead, the numeric action level compliance deadline is this fall, September 1 in 2023, and that's the top line with the two circles shown. But for the numeric effluent limit for copper, that's not going to come into play for another 9 years in 2032. So if you're working on projects in those areas, certainly very important compliance deadlines that you need to be aware of. And also just to be aware that there is a new provision to allow total suspended solids as a surrogate for some TMDL pollutants, and that process and the process and procedures that will be used are currently under development, and the permit will be modified and amended at such time when that work's done. So to wrap up the TMDL compliance requirements, the summary of our key points: 3 conditions must be met for TMDL compliance monitoring applicability. Recall that great figure that we have about slide 4 or 5. It shows the 3 conditions where the check mark in the middle, where it'll apply. Your project site has to discharge to an impaired watershed or water body. Your TMDL pollutant has to have been identified on your construction project site with a pollutant discharge. Your pollutant source assessment that you'll do as part of your stormwater pollution prevention plan, your SWPPP. And then during qualifying rainfall events, if you have a failure to implement BMPs or a breach, malfunction, or failure, or you've got a defined container spill or leak during that rain event, you'll have to do non-visible pollutant sampling and monitoring because of that. And then, of course, there's actions that you have to take, reports that you have to prepare if you exceed the values, and then, of course, consequences if you do exceed values, specifically for numeric effluent limits. You'll also need to apply appropriate erosion and sediment control BMPs to comply with the requirements per the order. CGP attachments D, E, and H describe this in detail. You'll have to clearly document those. We went through those during the presentation. You'll need to conduct the runoff sampling and monitoring using that non-visible pollutant sampling monitoring process that we talked in detail about, that's being amped up and really modified, if you will, to be more than just for NVP, also for TMDL compliance monitoring. And then you'll have to do the monitoring report, required exceedance reports, and conduct corrective actions if you do exceed action levels and effluent limits for attachments D and E. Thank you very much. Appreciate your time and attention. Best of luck.
Hello, my name is Andrew Sidor, and I will be presenting this module on the revised Universal Soil Loss Equation version 2. Russell 2 is not new to the 2022 CGP. However, its use is expanding in the new permit. This module will provide a very general introduction to Russell 2 and its role in notices of termination, compliance with TMDLs, and surface water buffer requirements. So Russell 2 stands for Revised Universal Soil Loss Equation version 2. It's a computer-based erosion prediction model that was developed by the United States Department of Agriculture and the University of Tennessee. And it's an enhancement from the original Universal Soil Loss Equation and Russell 1 version approach, combining both empirical data and process-based relationships. It was originally developed to support conservation planning. However, it is now more broadly used in construction to estimate erosion rates and sediment delivery. Russell 2 calculates erosion rates and sediment delivery through a wide variety of parameters. This equation on the screen here should look familiar to most of you. The major components in this calculation include climate, soil, topography, and land use. Starting with R, R is the rainfall erosivity factor. K is the soil erodibility factor. L is the slope length factor. S, the slope steepness. C is the cover management factor, such as the type and percent vegetative cover. And finally, P is the supporting practice factor. So think of stuff such as linear sediment control, BMPs. Looking at the graphics to the right, they provide a high-level understanding of how Russell 2 operates, starting with the simple slope you have soil loss and sediment delivery being equal, anything coming off the slope will be what is ultimately leaving your site. Moving on to the complex slope or concave slopes, they may allow for a portion of the detached soil particles to settle and deposit. So here you would expect your sediment delivery to be less than your soil loss. And then finally, looking at our slope with BMPs, we have C&P factors in Russell 2 that allow the user to model the addition of BMPs on slopes with the intention to reduce the soil loss and sediment delivery. Russell 2 does contain a vast database of these factors, allowing the user to prepare very site-specific models. The most common use of Russell 2 in the CGP is its use as a method for demonstrating final stabilization. This is very beneficial in arid regions where reestablishment of vegetation is often difficult. The requirements for use of Russell 2 as part of the notice of termination remain unchanged from the 2009 CGP. First, the discharger must model a representative number of slopes characteristic to the overall site. Both the post-construction soil loss and sediment delivery must be less than or equal to the pre-construction conditions. Site conditions must accurately match the entries in the computation, and this can be difficult determining the percent covers as it may be subjective from one user to another. Further, as part of the NOT submittal package, pre-construction and post-construction photos must be provided to verify the cover and management types used in the model. And finally, regional boards may require additional information such as contractor invoices, grading plans, and maintenance schedules to further verify that the calculations are correct and accurate. You can definitely expect follow-up site inspections from regional boards to verify that these conditions that have been modeled are true and accurate. Here's some example photos showing projects that use Russell 2 for termination of CGP coverage. Note that there are a variety of options available to use. So in the first photo here, we have hydroseed with hydromulch. You can use erosion control netting. And then finally, on the right-hand side, you can see that some long-term biodegradable structural controls like fiber rolls were used in addition to slope drains as a means of final stabilization. So all of these different techniques could be input into the Russell 2 model and used for your NOT. The one benefit of Russell 2 is that you may not have to wait for vegetation reestablishment. As these photos demonstrate, the slopes as they're shown in these photos did meet the post-construction requirement in the given conditions. New to the 2022 CGP is the introduction of Russell 2 modeling to achieve compliance with various total maximum daily loads, or TMDLs. Attachment H of the CGP describes the receiving waters that are subject to TMDLs requiring Russell 2 modeling. These include sediment TMDLs within Region 1, metals and toxics TMDLs in Region 4, and metals and toxics and nutrient TMDLs in Region 8. One specific thing to note on this slide and with the surrounding the TMDLs is that only certain receiving water bodies within these regions are subjected to these requirements. It's not a region as a whole. So highly encourage you to review Table H in Attachment H to see the full listing of water bodies that are affected with each of these TMDLs. So in order to achieve compliance with the TMDLs, the discharger must compare the soil loss and sediment delivery rates for representative slopes at various stages of construction with the pre-construction conditions. So the key here is really focusing on the various stages of construction. Similar to the NOT, use of Russell 2 for NOT, both the phased soil loss and sediment delivery rates must be less than or equal to the pre-construction condition. One thing to note here is the CGP further defines the construction phases as grading and land development, streets and utilities, and vertical construction. Once the discharger models these conditions, they must then also implement the modeled erosion and sediment controls on the site. We'll look at a couple examples on the following slide. So here in example 1, we will start by looking at TMDL compliance for a non-mass-based waste load allocation. This is simplified, demonstrating how a QSD could achieve compliance with the TMDLs through Russell II modeling. So first, the QSD must model the pre-construction condition of site slopes. Looking at the green highlighted row in the table, we show one such slope. We assume, or for our input parameters, we assume that a slope consists of mixed grass and shrubs with 40% cover. It also assumes that there are no additional controls in place. So assuming solely that vegetative cover is on the slope, we have no slope drains or other types of BMPs in place. So when we put these input parameters into Russell II, the output soil loss and sediment delivery is measured at 2 tons per acre per year. Now, this is going to be our baseline that we have to meet at the various stages of construction. So starting with the grading and land development phase, the QSD will need to replicate these slopes and see what our soil loss and sediment delivery is. So to give you an idea of what no controls in place and barren slope would look like, we go down to row 2. So one thing to note here is that the slope length and steepness has changed. This is common in practice. If you're doing a cut slope or changing any slope steepness, it is common to see changes in slope length and slope steepness. So making sure that we are accurately modeling that when it comes time to update for the phase of construction. Next comes an iterative process to ensure that the slope does not exceed the 2 tons per acre per year. So in its fully graded condition, we look at the bare soil condition with no additional controls in place. This results, the Russell II results in 19 tons per acre per year of soil loss, and similarly the same for sediment delivery. So clearly a much higher soil loss and sediment delivery than the pre-construction conditions, so we have some work to do. So the next step in the iterative process, let's assume the QSD decided to install a fiber roll or install fiber rolls spaced at 20 feet. Additionally, added a silt fence along the toe of the slope, and then also added a erosion control consisting of hydraulic mulch applied at 2,500 pounds per acre. This resulted in a Russell II output of soil loss at 2 tons per acre per year and a sediment delivery of 0.52 tons per acre per year, both of which are less than or equal to the pre-construction conditions. So in this case, this combination of BMPs, both the erosion and sediment controls, meets the condition of the pre-construction. So therefore, we are in compliance with the TMDL requirement. And then conversely, continuing on, the QSD would then continue to model the slopes during the remaining construction phases, making sure that each phase is less or has less soil loss and sediment delivery than the pre-construction condition. Example 2, we will look at TMDL compliance for a mass-based waste load allocation TMDL. So in this example, we'll assume the project's located in the Middle Fork Eel River watershed in Region 1. The project disturbed area is 14 acres. So in step 1, we need to determine the baseline soil loss and sediment delivery. What we'll do is we'll reference table H3 and attachment H. In doing so, we see that this particular watershed has a sediment waste load allocation of 23 tons per square mile per year. Now, since Russell II provides estimates in tons per acre per year, we need to convert this waste load allocation. So doing so, we end up with the resultant 0.036 tons per acre per year. Then we need to determine the site-specific waste load allocation. We multiply the watershed waste load allocation by the project disturbed area. So 0.036 tons per acre per year times the 14-acre disturbed area project site results in a 0.50 tons per year target for our Russell 2 runs. Once we have our site-specific mass-based waste load allocation, we need to determine the total sediment delivery for the site. To do this, we follow several steps. First, we need to break the project into drainage areas. Once drainage areas have been determined, we need to determine their weight in the overall project. This is done by dividing each drainage area by the sum of all drainage areas, or the total site size. And step 3 will determine, or once the drainage areas have been determined, we'll need to select representative slopes within each of these drainage areas. Typically, this will be paths, streets, or any major slopes within the drainage area. And each one of these will need to be modeled within Russell 2. After all the slopes within each drainage area have been modeled, we'll need to sum up the sediment delivery of all the slopes. In step 5, we'll then multiply the total drainage area sediment delivery by that drainage area's weighted average. In step 6, we will sum the weighted average sediment delivery of all drainage areas. And this will be the total sediment delivery for the project. This value must be less than the site-specific mass-based waste load allocation determined in step 1. And then finally, in step 7, once we've completed for the rough grade phase, or the grading land development phase, we'll repeat steps 2 through 6 for each additional phase of construction, so vertical construction and landscaping, or sorry, streets and utilities. Another use of Russell 2 in the 2022 CGP surrounds surface water buffers. Dischargers are required to maintain natural buffers when in water of the United States is within 50 feet of the site's earth disturbances. This is not always possible, so dischargers may use Russell 2 or a similar erosion prediction model to design and implement erosion and sediment controls that provide equivalent sediment load reduction. First, the QSD must model the soil loss and sediment delivery from the 50-foot undisturbed natural buffer. And then second, the QSD must select a combination of erosion and sediment control BMPs that result in less soil loss and sediment delivery than the baseline condition. So very similar to what we did in the NOT as well as the TMDLs. One thing that we should focus on is trying to preserve as much natural buffer or barrier as possible, and we can reflect this in our Russell 2 analysis. So going through a quick example of Russell 2 for a surface water buffer, assume the QSD models the soil loss and sediment delivery of a 50-foot undisturbed natural barrier. We'll assume that it's a 50-foot slope with 50% coverage of mixed grasses and shrubs. The resulting soil loss and sediment delivery is 0.19 tons per acre per year, as shown in the green highlighted row. So this 0.19 is our baseline for this project. In scenario 1, the discharger is, let's assume the discharger is able to maintain 30 feet of undisturbed natural buffer, leaving 20 feet disturbed. If this 20-foot section remained barren from earth disturbing activities, the soil loss and sediment delivery would be 0.69 tons per acre per year and 0.21 tons per acre per year, respectively, both exceeding the baseline condition. So the discharger or the QSD must go back and further refine the combination of erosion and sediment controls to get those values lower. So let's assume they went back, decided to add hydraulic mulch, applied at 2,500 pounds per acre, as well as placed silt fence along the toe of the slope. After modeling in Russell 2, looks like the combination of this 30-foot undisturbed area combined with the erosion and sediment controls resulted in soil loss and sediment delivery of 0.18 and 0.17 tons per acre per year, respectively, meeting the requirements. In scenario 2, noting that we might not always be able to preserve any portion of the natural buffer, Let's assume that we have to disturb all 50 feet. So looking at this, we have graded barren, no controls in place. Our baseline soil loss and sediment delivery is 1.20 tons per acre per year. With this added length of disturbed area, the discharger must now apply hydraulic mulch to the entire portion of the disturbed area, install fiber rolls spaced at 20 feet, and place silt fence along the toe of the slope in order to decrease the soil loss and sediment delivery below the baseline condition. So a summary of what we covered is Russell 2 is an erosion prediction model that allows users to determine both soil loss and sediment delivery from single slopes within their project sites. Russell 2 has been used to achieve notices of termination under the 2009 CGP and will continue under the 2022 CGP. Additionally, Russell 2 must now be used to model site conditions at various stages of construction for projects subject to certain TMDL requirements as defined in attachment H of the permit. Similarly, Russell 2 is to be used to model natural buffer equivalency for projects unable to maintain a 50-foot buffer when discharging to a water of the US or United States. The key to Russell 2 is that both soil loss and sediment delivery rates at certain project milestones must be less than or equal to pre-construction conditions. The QSD shall follow an iterative process in designing and implementing additional erosion and sediment control BMPs until this is achieved. And finally, backup documentation is always required when using Russell 2. This can consist of site photos. Russell 2 input and output should always be included. And further, the regional board may have additional requests and site-specific documentation. Thank you. That concludes the module on Russell 2.